What we're talking about is trees, which are kind of two-dimensional hierarchical data structure. Unlike lists, which we talked about last week, there's nothing about trees built into Scheme. It's entirely an abstract data type that you can build however you want. We're going to look at actually various alternative ways of doing it. But first, let me start with what are trees for? Why do we want a hierarchical data structure? First reason is to represent a hierarchy. So this is a small slice of the world tree. So there's actually a lot more countries than this that you don't see. But the first level is just the world, and then there are some countries, and some countries we just hang cities off of, and in the US we have these things called states, and states have cities in them. And then there's this weird thing, which is the United Kingdom of Great Britain and Northern Ireland. And Great Britain is in turn divided into England, Scotland, and Wales, plus a couple of uninhabited islands. I think the last Manx person died a while back. And those have cities. So here's Liverpool, you know, the center of the universe. Notice, by the way, we'll talk about this in a bit, that there's a Cambridge, Massachusetts, and there's also a Cambridge, England. So that will get interesting in a bit. So one use of a hierarchical data structure is to represent a hierarchy. Duh. Here's another one. This thing is called a binary search tree. What makes it a binary tree is that each node has at most 2 children, and the children are explicitly divided into a left child and a right child. So 33 here has a left child but no right child, whereas 105 has a right child but no left child. Now, so that's what makes it a binary tree. What makes it a binary search tree is every node has the property that the nodes to its left underneath it are smaller than this datum, and the nodes to the right underneath it are bigger than this datum. Okay? That's what makes it a search tree. Now, there's nothing inherently hierarchical about these numbers. It's not that, you know, 25 plus 92 adds up to 47 or anything like that. The position of numbers in the tree is kind of arbitrary as long as it comes out pretty well balanced. You know, you throw things in at random, it probably will come out pretty well balanced. The value of the hierarchy is if we want to do a search for something that's in this tree. Remember, searching through a list takes time theta of n, proportional to the number of elements. So let's say I'm looking for the number 70. So I look at 47. I say 47 is smaller than 70. Therefore, I don't have to look at any of these, because they're all smaller than the number I'm looking for. So now let me look at 92. That's bigger than 70. So I don't have to look at any of these. So now I look at 81. That's bigger than 70, so I don't have to look at this. I look here. That's less than 70. And so I look at its right child, but there isn't any. And therefore I know that 70 is not in this tree. And to find out, I only had to look at 4 nodes. Okay? So searching in this tree turns out to be theta of log n. We use LG as an abbreviation for log to the base 2. So that's where we're using a hierarchical data structure not to represent a hierarchy, but to represent an ordering in an efficient way. Okay? And then finally, over here, we have what's called a parse tree. And this one represents the expression that you usually see written as 3 plus 4 times 5. That's what's called an in-order traversal of the tree. We'll get back to this later. I started on the left, then the node in the middle, and then the stuff on the right, and for that, recursively, it's left, middle, right. It can also be done in prefix form, where I start with the operator and then put the operands, and then we get plus 3 times 4, 5, a notation you've seen before in this course. And there's also postfix, in which I say 3, enter. So we're going to do the operands first. So here I'm done with 3. Now I do all this thing, operands first. 4, enter, 5, times, plus. And that notation is called reverse Polish notation. It's used by HP calculators. So all of these ways of traversing the tree are useful. Any compiler or interpreter for a programming language builds a structure very like this from the expressions that you type. No matter what the surface form of the language is, it ends up with a tree like this in order to do the compilation or the interpretation. Okay, so that's 3 different uses for trees.